Hi, everyone. I am very happy to say that we are now starting the 6th year of our AATRN's Topological Complexity Seminar. That's 5 years of diving into math together since we kicked off this seminar on October 22nd, 2020. Throughout this time, we've had the pleasure of hosting researchers from around the world and exploring many facets of TC. Thank you all for being part of this journey. I'm also excited to announce that our organizing team has expanded. Please join me in welcoming our colleague Ekansh Yahari from the University of Florida as a brand new member of the organizing team. So without any further ado, I'll hand the floor over to Ekansh, who will introduce our speaker for today.
Thank you so much. Welcome everyone to the Topological Complexity Seminar of the Applied Algebraic Topology Research Network. It's my pleasure to introduce Facundo Memoli from Rutgers University, who is going to tell us today about topological complexity and persistence. Please take it away, Facundo.
Thanks. Thank you very much for the invitation. And I should mention this is joint work with Ling Zhou, who is a postdoc at Duke University. So the motivation for us was how can we obtain quantitative versions of classical topological invariants, keeping in mind that we would like to eventually estimate the Gromov-Hausdorff distance between compact metric spaces. And for example, if we think of homology as an invariant of topological spaces, and thinking of homology with field coefficients, homologies are fairly rigid. We would be assigning to a space a single integer, the very number in some degree k of that space. And from the geometric perspective, one could argue that, for example, these two spaces, the circle and then the circle with a bunch of tiny little circles attached to it, are fairly similar, yet the very ones are different, and very different if I add many tiny circles here. So then the goal is to try and find a way to make homology and also other invariants more continuous. And the way that I'm going to present these ideas to you will be from the perspective of homology first, and then try to extract some framework that can be applied to other invariants. Jesus asked me to concentrate on some of the aspects that are more quantitative and things that are perhaps hopefully interesting to this community. So how do we go from homology to persistent homology? Well, let me tell you one very compact one very compact strategy for doing this. So we start with a compact metric space X, and the first step is to associate to X a thickening of X. That's why I use the letter T. And the dot is supposed to mean that for every pair of indices, S and T, real numbers, with S upper bounded by T, I have a topological space for every S, a topological space for every T, and then a map between them, which today I'm going to assume is an inclusion. And my notation here will remember the underlying space X of the filtration, and then also the indices, S and T. So we have a one-parameter family of topological spaces that we also call a filtration. And the classical example in geometry is the Vietoris strips simplicial complex. For a given parameter T, one looks at all the finite subsets of X, whose diameter is strictly bounded above by T. And this definition automatically satisfies this inclusion here. Because if you increase from S to T, you have more subsets satisfying that condition. And one requirement in this type of constructions is that the assignment from a compact metric space to this family, one parameter family of thickenings, we want that assignment to be stable in a suitable sense. So eventually, I'm going to get to tell you how, what is one strategy for doing this. After we have a thickening, in the context of persistent homology, we apply homology as a functor to every element in the sequence and also to every morphism connecting two elements in the sequence. So for S upper bounded by T, we get a diagram of this type in VEC. And the factoriality of homology tells us that we have this nicely induced map between these two vector spaces. So the next step is that one defines the so-called persistent Berry number of the filtration, which assigns to every pair of comparable elements S and T the rank of this map at the level of vector spaces. And in summary, we have a way to assign to every closed interval of the real line a pair S and T with S upper bounded by T, an integer, which is a rank of the corresponding map. And for example, when T and S are equal, we are going to obtain the kth Berry number of this topological space. Any questions so far? All right. Wanted to mention, give a few historical remarks here. The idea of making homology more continuous in the context of TDA and persistent homology goes back a couple decades. It can be found in the work of Frosini Landi Ferri from the University of Bologna in the early 90s. Then Vanessa Robbins wrote a PhD thesis where the idea was also explicit. And then Adelsbrunner and colleagues also identified ideas that are quite related to the notion of persistence. Now, going back to this idea of taking the rank of the maps induced at homology level. So here are two remarks that are going to play a central role in the generalization that we are after. So suppose that I have this diagram in top. So we have four spaces and then maps connecting successive spaces. Then the rank of the map induced at homology level by the composite map is upper bounded by the rank at homology level of this map. So we have monotonicity for obvious reasons, right? Because you have a commutative diagram, etc. And we also have this other elementary property that if we have two maps that are homotopic, F1 and F2, then the result of this invariant applied to them is going to be the same. So we have invariants with respect to homotopic maps. The next step in the hierarchy is to try to express stability for all the constructions that I mentioned. So we start with compact metric spaces. We would like to have a notion of distance between them. Then we induce for each of these two compact metric spaces thickenings or filtrations. And we would like to have a notion of distance between them so that this inequality is true, perhaps by paying constants or exponents. And then we would like to have a notion of distance between functions from int, from the collection of all closed intervals into the integers, with the property that we also have this inequality. So this is a sort of pattern that I would like to describe, how to construct each of these distances and how to prove these inequalities, and later how to be able to invoke very similar structures for invariants other than the invariant obtained by taking rank of the maps that you see at homology level. So starting from here, the persistent rank invariant is a function from int into integers. So we metrize a collection of all such functions through the so-called erosion distance. So suppose you have two such functions, f and g. Then for every interval, for every closed interval, consider its epsilon thickening. So the epsilon thickening is simply enlarging the interval by epsilon at each of its endpoints. If the interval I is a purple interval, so then I epsilon is going to be this interval, where I just elongated the interval on left and right by epsilon. And the erosion distance between f and g is infimal epsilon, such that f applied to the thickened interval I is upper bounded by g applied to I, and also conversely when I swap the roles of f and g. This is quite similar structurally to the definition of the Hausdorff distance, but it's nevertheless directly tuned to comparing functions of that type. And this notion is due to Patel. So the theorem that one can prove for the persistent very numbers is that the erosion distance between persistent very numbers of x and y is upper bounded by an interleaving type distance between the filtrations. I haven't yet told you anything about these sort of interleaving distances, and that's a subject of the next slide. Suppose you have two filtrations, t dot of x, t dot of y. Then let's look for the infimal epsilon with a property that we can find a one-parameter family of maps, phi sub dot, from t dot of x to t dot plus epsilon of y. And another family psi dot from t dot y to t dot plus epsilon of x. What I mean by that notation is that for every t, I want to have a map phi t from t of x to t plus epsilon of y. So I really want a system of maps, one for every t, and also something similar for the psi maps. And I want these maps to be continuous, and I want them to satisfy some commutativity up to homotopy. So let's delve into that. So fix a parameter t. So then we have t sub t of x, and the map phi t takes me to t plus epsilon of y. Then the map phi t plus epsilon, these two indices are the same, increases this index by epsilon. So it takes me to t plus 2 epsilon of x. Now between this space and that space, I have this inclusion. The inclusion from t to t plus 2 epsilon corresponding to the filtration of x. And I also have this map, and I want these two maps to be the same map to homotopy. So we have a symmetric condition that we obtain when we swap the roles of y with x. I believe this one doesn't need explanation, only that it is identical to this one after you swap the roles of x and y and phi and psi. There are two more conditions. These will be conditions 2 and 4. And let me tell you about condition number 2. So you fix two parameters, s and t, and then you have ts of x, tt of x, and then the inclusion from s to t corresponding to the filtration of x. Then you travel through the map ts, and you arrive at ts plus epsilon of y. You travel through the map, this one should be a phi, through the map pt from here to here, and then you also have this inclusion. This inclusion is the one corresponding to these two indices for the filtration y. And then you demand that this diagram commutes up to homotopy as well. And then this one is a mirror image of that one when you swap x with y. The interleaving distance between these two filtrations is the infimal epsilon, for which I can find maps, PMC, satisfying these four conditions. It's also useful to introduce some terminology. We say that an epsilon homotopy interleaving is any pair phi dot psi dot satisfying these four conditions. Okay, any questions? I should say that many of you might have seen the definition of or the expression for the interleaving distance in the category of vector spaces. Just want to remark that here we are producing this notion of interleaving in top, and it is therefore natural to seek a type of commutativity that is softer than the one that you typically require at the level of vector spaces or groups.
So Facundo,
so yeah.
So this set of epsilons for which you are taking the infimum, that would be in an interval, right? An interval to the infinite to the right.
Yes, correct. I mean, and I guess I should say something just to preempt another question. It could be that di is infinity, right?
Okay.
So we work with an extended pseudo distance, because what if the filtrations are never homotopy equivalent, and then there may be no epsilon satisfying these conditions. So this is an extended pseudometric in general.
All right.
And just to try and convey some intuition regarding this definition, let's look at the notion of zero homotopy interleaving, and hope that that helps us understand this definition a little bit better. So I just want to repeat that an epsilon homotopy interleaving is any pair phi dot psi dot satisfying these conditions. And then I'm wondering, what does that boil down when epsilon is zero? All right. So if epsilon is zero, looking at the first diagram, that means that, well, epsilon is zero here, so then this collapses to the identity between from t sub t of x to itself. So we have this self loop. Then I have the map phi t, and this map becomes psi sub t, and I have that map. So then to say that this commutes up to homotopy means that exactly I have this homotopy. And something similar happens when you look at the way that this other diagram collapses when epsilon is zero. So I'm going to have this condition for every possible t. So notice that the order of psi and phi change. And what about the parallelogram conditions? When epsilon is zero, these arrows become vertical. So we obtain this item here that tells me that the square commutes up to homotopies, and the arrows connect S with S. You don't have this land anymore. And the same thing happens for the mirror image of that diagram. So then a zero homotopy interleaving is a natural homotopy equivalence between these two filtrations, right? And computing, or trying to compute this infimal epsilon measures the degree to which two given filtrations are not naturally homotopy equivalent. So this is a way to quantify the failure of this and that to be naturally homotopy equivalent. Does that make sense?
Yeah. Would this interval be closed in general? Does it have to be closed, or?
I think that very greatly depends on the semi-continuity properties of the filtration. And since I'm not imposing any condition on them, I would say no.
Okay, thanks.
Yeah, so the semi-continuity properties matter, right? Because things can change rather abruptly, and what is the openness condition that you have at a given point? Okay, so this is a notion of distance between filtrations that we have, and I want to make a few remarks. Di is an extended pseudometric, so it may attain the value infinity. And should I say pseudometric? And maybe I forget the precise terminology, but what I mean today by pseudometric is that it may not satisfy the triangle inequality. There's something clunky about the definition that I don't have too much time to delve into, but let me just say that I opted to work with this definition during the talk because it simplifies the presentation quite a lot. But if you want to see the real thing, I suggest you look at this paper by Blumberg and Lesnik, where they define the homotopy interleaving distance, which has a better behavior in terms of the triangle inequality, or this other paper joined with by Frosini, Landi, and myself, where we introduce another notion called the homotopy type distance that is closely related to this one. Nevertheless, this clunky definition permits somehow giving a very concise description of the main ideas. Also, historically, I want to point out that the notion of interleaving was already present in results that Frosini and company obtained in the 90s. Vanessa Robbins also identified a very similar notion that she used to prove the stability of persistent Berry numbers. And then this was formalized and extended in work by Kohensteiner and company in 2007. And then the conceptualization of the idea of interleaving distance and the name itself was given by Chazal and collaborators a few years later. And I should also mention that Peter Bubenik then did more work on trying to generalize those ideas. Peter Bubenik and collaborators. Yeah. Okay, so we have now a precise definition for the erosion distance. And we also have a precise definition for this interleaving distance between filtrations. So what I wanted to show you now is how we can prove this inequality. And the way that I want to motivate this inequality, or the way that I want to describe the intuition behind it, is that, as I mentioned at the beginning, we cannot expect that Berry numbers behave in a stable way. But if we do this trick of now creating a function from intervals into integers that softens the Berry numbers, then they become stable. So the persistent Berry numbers will be stable relative to that notion of distance, the interleaving distance. So let's take an eta such that eta is an upper bound for the interleaving distance between Tx and Ty. So that means that we can find maps. And I see that I made a little mistake here. Maps P dot MC dot satisfying the 4 conditions in the definition of the interleaving distance. And I want to claim that using the maps and the fact that they satisfy these 4 properties, I can then prove that the following diagram commutes up to homotopy for every S upper bounded by T. So let's see. So we pick S and T with S at most T. Then we look at S minus eta. And we also look at T plus eta. So horizontally, we have this inclusion that is given to us by the filtration Ty. And we also have this inclusion between Ts of x and Tt of x. The interleaving maps give me this map from here to here. And the other interleaving map, phi, gives me a map from here to here. Now, if we use a commutativity up to homotopy of this diagram, then we have the following. So remember that the persistent Berry number of y in degree k in this interval is by definition the rank of the map at homology level induced by this inclusion. And because this map is homotopy to that one, then I have an equality between here and here. And because rank is a monotonic, the rank of this composite, or the rank of the maps induced at homology level by the composites, is going to be upper bounded by the rank of the map induced by this intermediate step. And that's the persistent Berry number of the interval I, which is the interval from S to T associated to the space X. So we start from Y, and I look at the persistent Berry number applied to the eta thickening of I, and I obtain that that is upper bounded by the persistent Berry number of X applied to the interval I. So in summary, we obtain this inequality. And this is true for every possible I interval, closed interval. And of course, by swapping the roles of X and Y, I obtain the other inequality that I need to conclude that the erosion distance is upper bounded by eta. And because eta was any number controlling the interleaving distance, we obtain the claim namely that this is upper bounded by the I. Are there any questions about this? Okay. So now let's look at the claim, namely that this diagram commutes up to homotopy. So to prove that, I'm going to break this diagram into two subdiagrams, a triangle and this parallelogram. So let me go back. So I'm going to use this diagram and I'm going to paste it to that one so that this triangle will fit here, and then I will have this transition between the desired points. So this map can be obtained is equal to the composite of this map and that map. So here I'm inserting this topological space, which is intermediate between that one and that one in the filtration, is T as S plus eta of Y. And then the map phi, or the family of maps phi gives me a way to go from that space to that space, so that this triangle is commutative up to homotopy. And then that parallelogram will also commute up to homotopy. So then we immediately obtain the following, that this map being equal to the composite of that map with that map. And now using that this map is homotopic to that one, which is, sorry, I wrote it here, yes. So this map is homotopic to that one. And then I look at this map. And that one is homotopic to that. So we obtain the homotopy that I claim. Any questions about this? So now the question is, having seen this detail for a very simple case of the persistent varying numbers, the question is, how might we generalize this proof to other invariants beyond rank of maps obtained at homology level? So the properties that were used can be summarized in this way. Suppose that I is this tentative invariant. So then we use the fact that, or we would use the fact that the invariant applied to two homotopic maps is the same, and that whenever you have four spaces connected by continuous maps in this way, then the invariant applied to the composition is upper bounded by invariant applied to the middle step. Certainly, the persistent varying number satisfies that. And the proof that I showed you can be made to work for any I satisfying these two synthetic conditions. I want to point out that condition number 2 would be implied by condition 2 prime. It's not necessary to look at diagrams with 4 spaces to imply that condition. Is enough to contemplate diagrams consisting of 3 spaces and 2 maps. And the condition that implies that one, or one condition that implies that one, that is very simple, is this one, is that the invariant applied to G of F is upper bounded by the minimum of the invariant applied to F or the invariant applied to G. Now, we realized some time ago with my co-author Ling Zhou that a lot of invariants had emerged in the context of the LS category or cap length or topological complexity and the zero-divisor cap length. All the invariants that, or many of those invariants that are extended to morphisms appear to satisfy these conditions. For example, for the LSCAT, I think dating back to the 60s, Bernstein and Ganea already identified these properties. or the LSCAT of maps. For the cap length, this is something we did by hand with Conte Soto, Stefano, and Chao. We defined the persistent cap length or the cap length associated to the inclusion from S to T in a filtration in this manner. We looked at the image of the map induced at cohomology level by the inclusion, and then we looked at the length in the sense of rings of that image. And we verified without knowing that the whole world existed in relation to these maps that we could have those two conditions and therefore induce stability for the resulting persistent cap length. And recently, we started wondering, could it be that something similar can be done for topological complexity, which we knew to be conceptually related to the LSCAT, yet we had not explored? And it turns out that we found that Jamie Scott, a PhD student in University of Florida, and also Murillo and Wu had identified a notion of topological complexity for maps. So that's when we thought, well, maybe we can obtain better bounds for Gromov Hausdorff if we provide a rendition of the stability theorems when we utilize topological complexity instead of the persistent Berry numbers or the persistent cap length. So following the description that Jamie Scott provided in his PhD thesis and then in a paper that he wrote, if we have a continuous map between two topological spaces X and Y, the TC of the map F is a least natural number n, so that you can cover X cross X by n+1 open sets U1 to UN+1, so that for each of them, you have an F motion planar. And I think that in this community, Jesus told me that I won't need to explain this definition, but anyway, I'll let it be for a few seconds on the screen. And Jamie Scott also verified that topological complexity of the identity map on a space is equal to the topological complexity of the underlying topological space. And also this condition that is a condition that is sufficient to induce monotonicity in the sense that we needed for the stability proof was also established by Scott. And then also the invariance to homotopies was already established by Jamie Scott. So by using the exact same proof that I showed you, we can obtain the following proposition. So let me define, before reading the proposition, let me define something that we might call the persistent topological complexity. So given a filtration T dot of X, and given an interval, closed interval on the real line, say that your interval is exactly the interval from S to T, then look at the structure map or the inclusion from S to T in that filtration and compute the topological complexity of this as a map and associate that number to the interval I. So let's call that persistent topological complexity. So then you do that also for Y, compute erosion distance between them, and that is upper bounded by the interleaving distance of homotopy type that I described before. So I want to repeat that using the same pattern in the proof. This is obtained for free. So this persistent topological complexity is a map from int into integers. And visually, the way one can think about it is that, well, every interval is a per ST. So in the plane, in the upper part of the plane, so we have all the possible intervals are points with that representation. And then we would plot this as for every point we have an integer. Right? So it's very similar to the way the persistent Berry numbers or the persistent diagrams are expressed. Now, there's something that I mentioned at the beginning, which is that for us, the main motivation was to construct estimates for the Gromov-Hausdorff distance between compact metric spaces. So I wanted to now move to that part of the talk. So the notion of thickening that we tend to prefer when working with compact metric spaces is the so-called Vietoris-Rips thickening that I mentioned before. And I used this expression proto-theorem at some point. I want to go back to that. Here. So this is the plan for the talk, and I already described this particular inequality and all the constructions that intervene in that inequality. And now I want to talk about this notion of distance and also that inequality. So when we select T, the thickening, to be equal to the Vietoris-Rips filtration, one can prove the following result. Twice the Gromov-Hausdorff distance between the spaces X and Y is an upper bound for the homotopy interleaving distance between the filtrations. Now, what is a Gromov-Hausdorff distance? So if you have X and Y to given compact metric spaces, look for all the possible maps phi from X to Y and psi from Y to X. And these are set maps. There's no continuity required from them. And this is important. And for every pair phi and psi, compute the distortion of the map phi, which I will describe in a minute, the distortion of the map psi, and then the co-distortion of these two maps. So what is a distortion? The distortion is actually something that would be better called the additive distortion of the map phi. So for every pair of points X and X prime in X, you evaluate the distance between the points in X, and then you evaluate the distance between the points, between the image of the point, namely the distance in Y. And then you look at the worst case error that you make by taking the supremum of the absolute value of the difference. Of course, the distortion of C is analogously defined. It's more interesting to talk about what the co-distortion is. So the co-distortion arises in the following way. First, pick a point X in X and a point Y in Y. That's a point X. And you produce the point phi of X from that point X. And now from the point Y in Y, you produce a point psi of Y. So now you have 2 points in X and 2 points in Y. And compare the distance between these 2 points as points in X to the distance between those 2 points as points in Y. Look at the absolute value of that difference and then at the worst case scenario, namely what is the biggest difference that you could find. So Gromov-Hausdorff is the infimum over all possible choices of set maps, PMC, of the maximum of these 3 numbers. And Gromov proved in the 80s that these are really well-behaved distance. Namely, it induces a legitimate distance on the collection of all compact metric spaces modulo isometries. And it's also rather soft in the sense that if you have that X is a subset of Y, and you endow X with the restriction of a metric on Y, then the Gromov-Hausdorff distance between X and Y is upper bounded by the Hausdorff distance between X and Y. So for example, an epsilon net of Y, if X is an epsilon net of Y, then this will be upper bounded by epsilon. So that means that if you have a sphere and then you take away points from the sphere, the distance is very, very tiny. So I wanted to now spend a few minutes trying to convey some intuition about the meaning of this definition, especially about these three numbers: distortion of phi, distortion of C, and the co-distortion between phi and C. Now, the interpretation of distortion, I think, is fairly clear. If you only had to infimize that value, you would be looking for a map phi that is as isometric as possible. The same thing would be true for that particular quantity. So it's the thing that I really want to explain is the meaning of co-distortion. So the co-distortion of the pair phi psi was, by definition, the supremum of this quantity over all points x in x and y in y. So let's assume that that is upper bounded by some number zeta. So that means that then for every x in x and y in y, we have that dx between x and phi of y minus the y of phi of x and y is upper bounded by zeta. So in particular, if we fix x and we let y be equal to phi of x, in that case, we obtain the distance between x and psi of phi of x minus distance in y between phi of x and phi of x again. And because we're working with metric spaces, that value vanishes. So then what we have is that the distance in x between psi of phi of x is at most zeta. So that means that co-distortion controls the extent to which, the degree to which these two maps are inverses of each other. Right? I could also, similarly, I could obtain dy of y, d of c of y, upper bound by eta. So then that means that co-distortion being bounded by eta means that phi and psi are eta close to being inverses of each other. Let me see what's next. Yeah. Now, the theorem that I claimed before, namely that Gromov-Hausdorff distance between x and y upper bounds the interleaving distance between Vietoris Rips filtration of x and Vietoris Rips filtration of y, requires me to do the following. So on the one hand, I will have spaces x and y and these maps with a property that these two maps are very close to being the same, and these two maps are close to being the same, and that these maps have low distortion. Now, I need to convert these possibly discontinuous maps into continuous maps, in families, a family of continuous maps, right? There's something that we don't, there's no time to discuss today, but the transition between these maps that could be possibly discontinuous and the ones that I really need to control interleaving causes a little bit of a headache. But anyway, that's something that the community has found ways to deal with, actually. So it's not a real problem. It's just a conceptually interesting step. Anyway, as a corollary of everything that I mentioned today, we have the following. On the one hand, this inequality, and because of the inequality between interleaving distance and erosion distance for the persistent Betti numbers, I get this sequence. Twice Gromov-Hausdorff upper bounds that number, and that upper bounds that number. So in particular, we obtain that this is a lower bound for Gromov-Hausdorff. The erosion distance between persistent Betti numbers could be a reasonable lower bound when you're trying to estimate Gromov-Hausdorff between metric spaces. But by using very similar techniques and ideas, we also obtain this lower bound for the persistent topological complexity. And this is one reason why we got ourselves interested in the notion of topological complexity. We were wondering, well, there are cases in which persistent homology doesn't give me a very good lower bound for Gromov-Hausdorff. So then we were trying to find other possible invariants for which these sort of lower bounds would be better. And that leads to a very natural question. What are examples, or what examples showcase that persistent topological complexity might perform better than persistent homology in the task of obtaining lower bounds for the Gromov-Hausdorff distance? And here's the example that I wanted to mention. So let's consider RPN and the wedge sum of spheres S1, S2, all the way up to Sn. So they have the same homology when we use F2 coefficients. So you would expect that because of that fact, then maybe persistent homology will not be so good at differentiating them in a quantitative sense. So let's see how much better we can do with topological complexity at obtaining a lower bound for the distance between them as metric spaces. But then the question is, how do we view X and Y as metric spaces? What sort of metric do we use here, and what sort of metric do we use there? So for RPN, namely for my metric space X, let's consider the n-dimensional sphere, the round n-dimensional sphere with radius 2. And we endow this sphere with a geodesic distance. So namely, the distance between 2 points is just the angle between them. And then we give to this quotient space the quotient metric, so namely the quotient of the geodesic distance under the Z2 action. And for the wedge sum, things are a little bit more complicated to explain, but let me say the following. So to each SI, well, each SI as a metric space will be the unit round sphere. And we give to that SI its geodesic distance. And then we use the so-called gluing metric. So the gluing metric is exemplified here in the case that n is 2. So pick a point on S1 and pick a point on S2, and then glue that point to that one. In the sense that if you wanted to know the distance between X and X prime, and X and X prime are placed like that, so then you would just compute the distance on that S1. But if you wanted to know the distance between X and X prime, now the point's in red, the recipe for that, according to the gluing metric construction, is to go from X to the common point, and then go from the common point to the point X prime. So that's the way in which we view RPN as a metric space, and the way in which we view the wedge sum of spheres as a metric space. Are there any questions about this? All right, for these choices of metrics on RPN and on this wedge sum, which they seem fairly natural because we didn't do anything strange, maybe only that we took a rescaling of the sphere here. Using those choices for the metrics, we obtain that the erosion distance between the persistent topological complexity of RPN and the persistent topological complexity of the wedge sum is lower bounded by pi by 3. So there's a very detailed calculation that permits obtaining that estimate, which in particular means that the Gromov-Hausdorff distance between the two spaces will be lower bounded by pi by 6. Remember that in the stability theorem, there's a 2 multiplying Gromov. And in a collaboration between Ling and Aníbal Medina Marrones, they proved that the erosion distance between the persistent varying numbers for these two spaces is upper bounded by pi/4. So which tells us that topological complexity is a better bound in a quantitative sense between the two given spaces. Are there any questions about it?
Did you mean in the previous slide, Facundo? Did you mean the? No, that's the next one. Where is it?
This one?
That one. That one. So the second inequality, it's the other way around.
Yes, it's the other way around because it's what we wanted to emphasize is that this is upper bounded by pi/3 and upper bounded by this. Simply to say that topological complexity wins in this competition, if you know what I mean, right?
Yeah. Okay. Thank you.
And I maybe in 2 minutes I will say just how very, very briefly how the calculation is organized. This one here. So for a given interval I, remember that the persistent topological complexity takes as input an interval I and produces a natural number. So if the interval I is contained in the open interval from 0 to 2 pi/3, we, by combining several results, in particular some results by Farber, Tabachnikov, and Juspinski from 2003, and then some results by Adams and colleagues, that this number will equal the topological complexity of RPN, which in this paper, they proved to be lower bounded by 2, strictly. Now, as for the persistent topological complexity of the wedge of spheres, when the interval I is contained in the open interval from 0 to some number zeta n that I will mention in a second, the topological complexity will be 2. And this strict inequality in comparison or in relation to this equality is what will give access to this number. The number zeta n here appears as a filling radius of spheres. So that's the so-called Gromov's filling radius of Sn. And it's equal to the arc cosine of -1 over n+1, which is upper bounded by zeta 1 when, this number decreases when n increases, and therefore it will be upper bounded by zeta 1, and zeta 1 is a cosine of -1 over 2, which is 2 pi/3. And 2 pi/3, just by coincidence, is equal to that number. So exploiting this relationship between the different parameters that appear, we are able to prove the lower bound pi/3 by looking very carefully at the definition of the erosion distance.
So Facundo,
yeah, so here's my picture. Yeah. Mm-hmm.
This is very, very, very intriguing because you're having this improvement just by using the fact that the topological complexity of RPN is higher than 2, though it is usually much higher than that. It's roughly 2n minus something on
yeah.
So what would you expect that if you use a better bound, general bound, would you get a better improvement?
No. I mean, the thing that makes a difference is that these two numbers are simply not the same, and that the ranges inside of which the numbers are not the same differ. So the techniques, or say the lower bound that we proved using erosion distance, doesn't see the multiplicity, doesn't see that number. It only sees that the numbers are different. And that is quite closely related to something that many of you might have seen, that in standard persistent homology stability, the typical lower bound that people use is not erosion, but it's the so-called bottleneck distance. So there's a chance to improve some of these lower bounds by invoking stronger notions of distance between persistent invariants. But in the one that we worked out for erosion distance, we cannot really exploit yet the gap. Only the existence of a gap is what matters. I mean, sorry, apology. I don't think I can explain that too succinctly, but I guess I'm stating a fact. Yeah.
That's okay. Thank you.
Yeah, but anyway, so this is a graphical representation of the way the information looks like. I was trying to say that the region inside of which you have a value larger than 2 is larger than the region inside of which you have a value of 2. So, and remember that I need to be able to control this invariant by that invariant. So if I pick that point, if I pick that interval, then I need to ask myself, by how much do I have to enlarge the interval so that I make this small, right? And well, it will be at least a difference between zeta n to pi by 3. So by doing these sort of observations, you can get this lower bound. Anyway, I reached the end of the material that I wanted to share with you. My goal was to try and explain how it is that we utilized invariants related to topological complexity in our search for effective bounds for Gromov-Hausdorff between compact metric spaces. Thank you.
Thank you. Thank you very much, Facundo, for this very nice talk. Are there any questions from the audience, please?
Well, I have one question. So the one way of seeing the difference between RPN and this wedge of circles is, of course, the multiplicative structure in the cohomology cup products. And somehow the computation of TC through the lower bound given by zero divisors cup length takes that into account. So I was wondering if have you thought of any other examples where this drastic difference between multiplicative structures are not present? Say multiplicative structure in the cohomology is more or less similar, but still maybe TC is better behaved?
No, we haven't. I mean, I at least I don't remember right now having gone through any example with that particular feature. But thanks for the suggestion. That could be interesting.
Yeah. So is there any kind of multiplicative topological persistence taking into account cup products?
Yeah. So a very similar set of claims can be made for the cup length, or for something that you can call persistent cup length. And at the same time, for the zero divisor cup length, you can also induce a persistent version of that. We have actually included that into a preprint that's already in the archive. Let me see. So I might have mentioned that somewhere. Well, I mean, the short answer is yes, you can. So the persistent cup length is something we looked at a few years ago, and it's fine. I mean, you can prove stability and utilize it to discriminate spaces. And in the same preprint that I described today, we looked at the zero divisor cup length as in a persistent manner. The analysis that Jamie Scott did was fairly useful to us. I think that most of the properties we needed were already established in his thesis, except for one little step that we had to do to prove the monotonicity. Yeah, sorry, I don't think I wrote it into my slides.
All right, thank you.
Are there any other questions? If not, then perhaps Jesus can stop the recording and people can still jump in and ask the questions and carry on the discussions. Thank you. Let's thank the speaker again, please.
Thank you.